Okay, class, so let's go over the pyruvate dehydrogenase multi-enzyme complex. This is an important enzyme that aerobic organisms utilize to take pyruvate and convert it to the high-energy molecule acetyl-CoA. So if we were to write what this enzyme catalyzes, it catalyzes the irreversible reaction. So the reaction arrow proceeds in one direction, and the reaction is pyruvate. Now this pyruvate came from glycolysis, converting glucose to pyruvate in the 10-step pathway known as glycolysis, plus this high-energy molecule known as coenzyme A, or CoAsh, because the thiol group really is the carrier. And this coenzyme A, there's a pool of this in the cell, will react with pyruvate from glycolysis. It is a dehydrogenase, so a dehydrogenase implies an oxidation reduction reaction. So in this particular case, NAD Plus, the oxidized form of NAD Plus, will get reduced to NADH. You also cleave off a CO2. So it also is a decarboxylation. And then finally that pyruvate, after the CO2 is removed and it gets conjugated to this high energy thiol group, you have acetyl-CoA. So this acetyl-CoA actually can go straight into the TCA cycle, okay, which is advantageous for aerobic organisms. Right. And another advantageous aspect of this multi-enzyme complex is the generation of reducing equivalents in the form of NADH. So remember, NADH can donate its reducing equivalents to the electron transport chain. So what is unique about this enzyme is that it's not just simply and the substrates go to the active site and get converted to products. This is actually a super enzyme, or in some cases a mega enzyme, that's organized in several multimers. It consists of enzyme E1, and enzyme E1 is the actual pyruvate dehydrogenase activity. So enzyme E1 is the actual pyruvate dehydrogenase. Enzyme E2 is activity, or contains activity known as dihydrolipoyl transacetylase. This actually consists of a trimer, whereas E1 pyruvate dehydrogenase is a dimer. And then finally you have E3, and that E3 is enzyme activity is dihydrolipoyl dehydrogenase. It really regenerates the lipoic acid cofactor back into its original form so that it can start another round of catalysis again. All right. So there are a number of cofactors that are involved in pyruvate dehydrogenase multi-enzyme complex. By the way, E3 is a dimer. So the way these things are organized, as stated before, this is a multi-enzyme complex. So these actually have multiple subunits. So this is a dimer, but it actually contains 24 subunits. This E2 core is a trimer, and it contains 24 subunits. And this E3 dihydrolipoyl dehydrogenase is a dimer, and it has 12 subunits. All right. So 12 subunits of the dimer for E3, 24 subunits of the trimer for E2, and 24 subunits of the dimer for enzyme E1. So E1 and E2 and E3 are all contained within pyruvate dehydrogenase multi-enzyme complex. So you can see by having these multimers, or a multimeric form of this enzyme complex, you can actually get a lot of substrate shuttling. So you actually proceed left to right here, as the way I have drawn it, in a very efficient manner. It's not just a one-to-one substrate goes to product, but you can have multiple substrates being funneled and channeled and expeditiously produce product. So this enzyme is sort of like a machine, and this machine has a number of subunits. Let's talk about 3 of the subunits that are contained within each of these enzymes that constitute the PDH Multienzyme Complex. The first one is TPP. Okay, that stands for Diamine Pyrophosphate. So that's the cofactor that's associated with E1. And then the cofactor that is associated with E2 is lipoic acid, but that lipoic acid is conjugated to the amino acid lysine. So actually we call it lipoamide. We also just call it lipolysine or lipolysyl, but the actual cofactor is lipoic acid. It's conjugated to the amino acid lysine. And then finally, the third cofactor contained within E3 is FAD. Okay, that FAD actually is associated intimately with a sulfhydryl group that's within the E3 protein. Okay, so FAD, lipoic acid, and TPP are 3 of the cofactors that are involved. So let me focus here on the lipoic acid. As I stated before, it is actually conjugated to the amino acid lysine. And if you look at the structure of lipoic acid, it is actually a long tether. Okay, and it's about 12 to 14 angstroms in length, but it's going to just be a very long stretch of a hydrocarbon chain, and then it ends with a disulfide bond. Okay, so that is lipoic acid conjugated to the side chain of lysine. It's actually conjugated to the epsilon amino group of the lysine residue. All right. And so that is form 1 of this long chain, about, as I stated before, 12 angstrom tether or 12 angstrom swing. Okay, so that is going to be associated with enzyme E2. Now let's talk about diamine pyrophosphate. Okay, so this contains thiamine, and thiamine is conjugated to a thiazolium ring. So the thiazolium ring actually has a carbanion component to it. It's a carbon which has a negative charge, or a negative formal charge, so it makes it exceptionally nucleophilic. So what happens is that this carbon, that is a carbanion, will actually be involved in carrying carbon units. All right, so I'm just going to put a carbon with the negative charge here. That is part of its structure. This is resonance stabilized, that carbanion, within thiamine pyrophosphate. All right. So the first thing that I would like to talk about is what happens in terms of this reaction. All right. So the first thing is, let's just write or draw the structure of pyruvate here. Okay. So the very first step in this reaction mechanism is that this CO2 is going to come off. Okay. The COO minus, the carboxylate group, is going to come off. Okay. And when it comes off, there is your CO2, and this acetyl group, which I'm going to circle right here. Okay, this acetyl group is actually going to be carried on this carbanion. Really what's happening is that this carbanion that's resonance stabilized as part of the TPP cofactor does a nucleophilic attack right here on this acetyl group, and the CO2 serves as the leaving group, and the CO2 comes off. So what happens then is that this carbanion from TPP, so I'll just call this TPP, this carbanion from TPP now becomes TPP with that carbon carrying the acetyl group, but it carries it in the form of a hydroxyethylamine intermediate. Okay. So you have a hydroxyethyl intermediate where TPP carries this acetyl group as a hydroxymethyl intermediate, or excuse me, a hydroxyethyl intermediate. So this is the hydroxyethyl intermediate conjugated to TPP. Okay, TPP conjugated to that C, CH3, and OH, hydroxyethyl TPP intermediate. All right, that is a result of this carbanion from TPP doing a nucleophilic attack on this acetyl carbonyl group. The CO2 leaves, and now you have a hydroxyethyl intermediate conjugated to TPP. So what happens next is that this E1, which has the TPP, carries the acetyl group, carries this acetyl group to TPP, and now this acetyl group in the form of the hydroxyethyl intermediate is going to get transformed, or transferred I should say, to one of the sulfurs, breaking this disulfide bond on the lipoic acid or the lipoyl lysine intermediate. Okay, that is associated with enzyme E2. So this is form 1 of the lipoyl lysine intermediate. Okay, lysine is part of the active site of the E2, which covalently attaches to the lipoic acid. So now what happens here is that we will have a transfer of the acetyl group in the form of the hydroxyethyl intermediate to form 2 of this swing. And now, attached to this lysine is this lipoic acid long tether, but now you have an SH group, and now you also have the acetyl group. Okay, now the acetyl group is attached to one of the ends of the lipoic acid, lipoyl lysine intermediate. So this would be form 2. Okay, so notice what we have done here. We have moved this acetyl group to TPP, giving a hydroxyethyl intermediate, and then from TPP it donates that acetyl group to reduce one of the ends of the lipoic acid side chain. All right, so this would be form 2 of the tether. Okay. So the next step in this process is to actually make our product, our very first product, and that is acetyl-CoA. So this is where our fourth cofactor comes into play, and our fourth cofactor is coenzyme A. So our first cofactor was TPP, our second cofactor was lipoic acid, and our third cofactor is FAD. So coenzyme A is going to come in. It's going to come in the form of CoAsh. So here comes coenzyme A. And now this lipoic acid will go into step 3 and donate that acetyl-CoA, or excuse me, that acetyl group to coenzyme A. So that is going to look like this. So here goes the acetyl group. Let me zoom in here a little bit here and try to show this to you in real time what's happening. Here is that acetyl group CH3C double bond O. Here is one of the SH group that has been reduced. One of the other S's is conjugated to the acetyl group. And now what's going to happen here is that this lysine residue attached to the lipoic acid will donate, or excuse me, this acetyl group will be donated to coenzyme A. So it goes to coenzyme A, and that produces our first product here, acetyl-CoA. This acetyl-CoA, this acetyl group ultimately came from pyruvate, which came from glycolysis. And now you have this high energy acetyl-CoA bond. It's ready to go to the TCA cycle. Okay. So now this has been donated to CoAsh to give you coenzyme A. What does this become? Well, this becomes the third form of the lipoyl lysine conjugate. And now attached to this lysine, this is going to look like this. It's going to have two thiol groups. Okay? And this would be step 3 of the swing. Okay? So after donation of the acetyl group to coenzyme A to give you acetyl-CoA, which can go into the TCA cycle, we're actually done. This lipoic acid cofactor, lipoyl lysyl cofactor conjugated to lysine, now has two thiol groups, two SH groups. Okay? Here's SH group 1 and here's SH group 2. Here's thiol group 1, here's thiol group 2. So we're actually done if you think about it, because we've made our product. We've made acetyl-CoA and we have CO2. But the real issue is, how do we get back to square one? Okay? How do we get back so that these two SH groups come back to the fully oxidized S disulfide bond? Okay? So how do we go from 3 back to 1 and recycle this so that everything comes back to normal? And that is where E3 comes in, the dihydrolipoyl dehydrogenase activity. Okay? So this enzyme actually has an FAD that is associated with 2 sulfahydryl groups. And so first of all, what happens is that these electrons are going to go and reduce the sulfahydryl group, or the 2 sulfurs in E3. So you'll get 2 sulfahydryl groups. So we go back here, and where do these 2 electrons go? Okay, these 2 electrons are going to go here. SH, SH. All right. And now how do we get this form back to the original form so that the whole catalysis can proceed again? Okay, that is where our 5th and final cofactor comes in, and that is NAD plus. So NAD plus, which is in a pool sitting around in the mitochondria, okay, what happens is that this SH donates its electrons to FAD, H2. So now we resume the disulfide bond, but FAD, H2 donates those electrons to NAD plus to give you NADH. And a proton comes along for the ride. And this just goes into the matrix pool. So it can donate its electrons to the electron transport chain, and this just goes around in the pool that's found in the mitochondria. So this is a mitochondrial, geographically speaking, a mitochondrially located enzyme. All right. So let's just quickly go over this again before we wrap this up. Okay. One thing is, it would be good if you're able to recapitulate this diagram and explain the steps. Let's just go over the steps here. Okay. First of all, we have E1 that contains thiamine pyrophosphate. Okay, if you look at the structure in your textbook or on your PowerPoint slide, it actually has a carb anion because that thiazolium ring is resonance stabilized. So this carb anion serves as a very powerful nucleophile. It will nucleophilically attack the C double bond O on the acetyl moiety, causing a decarboxylation. The TPP carries this acetyl group in the form of a hydroxyethyl intermediate. Okay, so hydroxyethyl intermediate. Okay, that's your TPP hydroxyethyl intermediate. Now, if we study the pentose phosphate pathway and looked at the transketoalases, more specifically, they are also TPP but dependent, and they will have a dihydroxy methyl intermediate as opposed to a hydroxyethyl intermediate. Okay, so that's basically alludes to what TPP does as a cofactor in cell. It's a carbon-carrying molecule. It carries the carbon for transient transfer to another molecule, okay, through the power of this carb anion. So that's for the pentose phosphate pathway. If we study it, you'll realize that TPP kind of does the same thing. Here in pyruvate dehydrogenase, we have a hydroxyethyl intermediate. And in transketolases in the pentose phosphate pathway, we have a dihydroxyethyl or dihydroxymethyl intermediate. Again, it alludes to the fact that TPP is a transient carrier of 1 carbon or 2 carbon units. All right, so as far as the hydroxyethyl intermediate, TPP intermediate is concerned, that transient transfer of the acetyl group to CoAsh, or excuse me, occurs through the reduction of one of the disulfides on this end of the lipoic acid chain. Lipoic acid is conjugated to lysine. And so the hydroxyethyl intermediate comes and is donated to the sulfur, thus breaking this disulfide bond. You regenerate the TPP so that it can occur for another round of catalysis. So step 1 of the lipoic acid chain. Here's step 2 in the swing. So this is going to be a swing or like a long tether. And then the acetyl group gets transferred to coenzyme A. So here's that acetyl group. Coenzyme A comes in. We have our first product, acetyl-CoA. Actually, our second product, if you consider CO2 as one of the products. And then this lipoic acid tether now has 2 SH groups. Again, we have swing in state number 1, swing in state number 2, a swing in state number 3. Look at the states of the sulfurs. Okay, completely oxidized disulfide. We have 1 sulfhydryl, 1 is carrying the acetyl group. Once the acetyl group is transferred, we have 2 sulfhydryls. How do we get back to the oxidized form of lipolysyl or lipolysyl acid, lipoic acid conjugated to the side chain of lysine? Well, those electrons are donated to the sulfhydryl group on enzyme E3, dihydrolipoyl dehydrogenase. So now we've regenerated the oxidized form of lipoic acid so that it can continue the process again, the E2 cycle. And then the electrons go from the sulfhydryl group to FADH2, and ultimately from FADH2 to NAD Plus to generate NADH, the final reducing equivalent and the final product, which then can then go into the mitochondrial matrix and serve its function within the matrix pool. All right. So the important thing to remember is that since these are organized in multiple subunits, this thing actually acts as a big swing. Okay, lysine, as you know, is a very long side chain. Okay, if we remember the structure of lysine, it is CH2, 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 and then an NH3 plus. However, as we stated before, that NH3 plus is now going to be conjugated to lipoic acid, and now you have a very, very, very long tether. As I stated before, it's about 14 angstroms long. Okay, so you can imagine, based upon the oxidation and reduction of these sulfohydryl groups, this lipoic acid swing or lipolysyl swing or lipolysyl tether will carry acetyl groups. It's just going to carry acetyl groups to coenzyme A and then regenerate the oxidized form by delivering those electrons to FAD, and FAD delivering those electrons to NADH, all of that mediated by E3. So you see, by having these in multimers, this can be in a perpetual swinging motion or tether motion, and this thing is just very, very long. Okay, so here's the side chain of lysine, and then on top of that you have this lipoic acid that is a part of E2. Okay, so lipolysyl arm, lipolysyl swing, however you want to call it, it's about 12 to 14 angstroms long, and it's going to carry acetyl groups. All right, and then E3 just transfers those electrons back to the final product, NADH. So one final word here. Okay, this E1 and E2 is basically an acetyl transfer. This E3 is just getting the electrons so that we can regenerate lipoic acid so that it can complete the process again. So this is just acetyl transfer through TPP, the hydroxyethyl intermediate. E2 gets involved to donate it to coenzyme A to give you acetyl-CoA, and then E3 just regenerates these electrons. So in this case, E2 to E3 is kind of like an electron transfer, if you really want to think about it in that regard. So reduced thiol groups become oxidized, electrons go to the thiol, reduce the thiol, those electrons from the protein reduce FADH2, and FADH2 reduces NAD plus to NADH, which is the final product. So CO2 one product, acetyl-CoA the other product, NADH the third product. This is an irreversible reaction, and it's committed to the TCA cycle. Irreversible reaction is also regulated. It is feedback inhibited by NADH and feedback inhibited by acetyl-CoA. So that is allostery, okay, the feedback inhibition. And another thing is that this is sensitive to phosphorylation. So phosphorylation on the E2 subunit actually inhibits the enzyme. Okay, that negates the activity of the enzyme. And that phosphorylation is regulated at a higher level, usually through hormones. Hormones will activate a kinase. That kinase phosphorylates many enzymes in the cell. This is one of the enzymes it phosphorylates, and that's going to cause a reduction in the flux through the PDH Multienzyme Complex. So a very important enzyme, an enzyme that commits itself to the TCA cycle, and an enzyme that is regulated by its own product, and it's also regulated at a meta level, at a higher organizational level, at the hormone level, through phosphorylation. and through these signal transduction kinases that we really didn't go over. We really don't go over. We really do not cover signal transduction in Biochemistry 1. All right, so the pyruvate dehydrogenase multienzyme complex. Make sure you're comfortable with this. Make sure you're comfortable with the mechanism. Make sure you know about this tether, this swinging action mediated by E2, and know its importance because, as we said before, very complicated mechanism, very interesting mechanism, but it is the gateway to the TCA cycle. A final word. PDH multienzyme complex also has an ortholog, and that ortholog is the alpha-ketoglutarate dehydrogenase complex. Okay, alpha-ketoglutarate dehydrogenase complex that is found in the TCA cycle, and then the alpha-ketoglutarate dehydrogenase complex that's found in amino acid metabolism, or amino acid catabolism, breakdown of amino acid, particularly leucine, isoleucine, and valine. So another enzyme, one of them that we have studied in the TCA cycle, also has this E1, E2, E3 mechanism. Okay, in this case, alpha-ketoglutarate dehydrogenase in the TCA cycle converts alpha-ketoglutarate, that's a decarboxylation, and it converts that to succinyl-CoA. So alpha-ketoglutarate gets converted to succinyl-CoA in alpha-ketoglutarate dehydrogenase in the TCA cycle. And the pyruvate dehydrogenase multienzyme complex for entering the TCA cycle, acetyl-CoA, entry point to the TCA cycle, pyruvate gets converted to acetyl-CoA. So you see orthologs, you see analogies. The cell utilizes E1, E2, E3, and these cofactors, and almost the same verbatim mechanism multiple times in metabolism. Okay, so that is the PDH multienzyme complex, and it's something that you should know and be comfortable with in elucidating either for a essay question or multiple choice question on an exam. Thank you.